Hello, everyone. Thanks for being here. Today I will talk about continuum model for content materials, especially focusing on the mono materials. The big picture is how we go from the microscopic lattice model, which are very accurate but very large, to effective model, which is a partial different equation that captures the low-energy physics. So mono material has attracted enormous interest because they have host many exotic quantum physics. Experiments has observed quantum physics like the superconductivity, correlated incident state, fractional quantum Hall effect, often within the same material platform. So what's striking is that this physics can be tuned simply by changing the geometric parameters like lattice mismatch or the twist angle. So this makes more material extremely powerful, and people expect to find equal material within the class for our future technology. So a useful way to think about mono material is that they are like Lego blocks, and there exists a very large family of material have layer structure from graphene, traditional microdiphotonite, hexagonal nitride, and so on and so on. And among those materials, actually many of them can be exfoliated into a monolayer, which means we can peel them down to the single atomic sheet. So once we have those layers, and we can stack them in different combination, orientation, and angles to engineer new quantum materials almost by design. So at the core of the mono material is a simple geometric mechanism. The when two layer has a small lattice mismatch or twist angle, the interference creates a long wavelength, more superlattice. So even though each layer atomic scale periodic structure, the combined system looks derived like a new length scale that can be tens or hundreds times larger. This scale is called mono scale, and the unit cell can be called the mono unit cell. The initial microscopic model for binary material is high binding model, and the Hamiltonian has a block structure. So it has two parts, so the interlayer part and interlayer parts. So while this model is very accurate, actually the problem becomes computationally expensive when the model itself becomes really large. So the central question is, how can we systematically reduce the level problem of this model to another model, preserving the relevant low-energy physics? So one way to think about this problem is from dynamic problem. So we start with the high binding model and with initial condition, where this initial condition is relevant to a low-energy state. And what we can do is we can rapidly show that the dynamic of the high binding model actually can be reduced to solving that problem to the another differential equation, which is like the Dirac type operator. So we're talking about this binary graph in the previous slides here, with the top layer and bottom layer actually very similar. But when we consider the filter structure, many things changes. And the interesting low-energy physics about the filter structure usually associates with one of the two layers. So in that case, it will be simpler to start from a high binding model for the dominant single layer physics. And actually, as a result, we consider new type of high binding model just use a complement as example to motivate this construction. So in this model, the key new feature is this high binding model does not just depend on the interorbital distance, but it also depends on local environments. So one way to see this is you can see that within this coupling function hxy, so x represents the coupling distance between two orbitals, and the y actually is one variable we call environment variable. It tells you about the environment, local environment of this coupling pair. So to validate this model, actually what we do is we can compute the tensile states for the 1D coupled chain, and for the reduced model and from the full model. What we can see is this blue curve shows you the vessel state for the 1D couple chain from the full Hamiltonian. And the orange one show you the vessel state from the reduced model. This is a new effective pi-binding model. And you can see that for the low energy parts, there's something flipped in the x-axis, but actually in this plot, there's a high energy parts, and the spectrum align pretty well, and thus indicate actually we're reducing the model in adequate. So looking ahead, what we want to do is we use this pi-binding model, derive a continuum model describing the low energy physics, and what we get is the whole pi-binding dynamics is reduced to a Fourier type operator. And this is what we have done for the 1D ether structure system. And next, we try to generalize the system, also the approach to the 2D system. And also, we try to use this approach to establish, also construct an interacting fermion model to study the many-body phenomena in the ether structure. I think that's all for the talk.